Hello everyone. Today we're looking at the problem digit operations to make two integers equal. This was question 3 in Biweekly contest 145. So the question reads that we're given two integers n and m that consist of the same number of digits, and we can perform the following operation any number of times. So we could choose any digit from n that's not 9 and increase it by 1, or we could choose any digit from n that is not 0 and decrease it by 1. So we also have to make sure that when we're doing this, any new number that we create during this process cannot be a prime number. So the cost of a transformation is the sum of all the values that n takes throughout the operation. So we want to find the minimum cost it takes to transform n into m using these steps, and if it's not possible, we're going to return 1. So looking at this example here, we have n equals 10 and m equals 12. So our goal here is to transform n, 10, into 12 without it ever being a prime number. And the minimum cost to do this would be 85. So the explanation is that we have to count this initial cost 10. So we are starting at 10, so we have to include this in our costs. Then the numbers we can transform to are 20, 21, 22, and 12. So adding up all of the values 10, 20, 21, 22, 12 gives us 85. And our transformation cost is just the sum of all those values, and this is the minimum that we could possibly get. So a lot of people, when they see this, might immediately think that we want to use a graph, which is a good impulse. And why use a graph? Well, let's just kind of draw it out. So if we start at 10, what could we do here? Well, we could take this 1 and we could increase it, so we'd get 20. And then what else can we do? Well, we can't really decrease this because that would be 0, 0, but we could go to 11. However, 11 is prime, so we actually cannot do this. So now let's look at 20. Well, we could go to 21. That's valid. Or we could go back to 10, but we're not going to do this since we already saw it, so we can keep going forward. Let's kind of explore another option here. So say we go here, we can go to 22, or we could go back to 11, but again, so you can kind of see that as we draw out these relationships, this kind of forms like a graph-like structure. So we should use a graph to kind of model all the possibilities that we can take and try to find essentially a shortest path between this n and this m. So I mentioned shortest path, and a lot of people might initially think of BFS. But this is wrong. We don't want to use BFS. And why is that? So BFS is great for when we want to find the shortest number of steps, right? So say we want to find the minimum number of steps to get from point A to point B. That would be a great use case for BFS. But here, we're actually concerned about cost more so than just the number of steps, right? And that kind of lends itself to being a weighted graph. So for a weighted graph, BFS is not really the best choice, and we want to use Dijkstra's. And I mentioned cost, and what does that mean here? Well, let's say that as we're exploring our graph, we run into two options. Say we are at a number 20, and so far we've seen, let's say, 5 costs to get there, right? And let's say we see another branch where we're at 20, but it took us 10 costs. So why would we ever want to explore this one, right? We're going to have all the same options coming from this one here, but we're starting at a lower cost. Whereas if we explored the options here, I guess we would get to the same numbers, but our cost would always be 5 more than if we just went with this one. So essentially what we want to do is we want to explore the options that have the smallest cost first. And this is a great use case for Dijkstra's algorithm, because what we can do is essentially we can pick the option that has the smallest cost, explore all that, and place those options onto a heap and just keep exploring those that have the smallest cost. And by doing this, we can guarantee that we will find the minimum cost way to get from our original n value to our target. So I mentioned that we want to use Dijkstra's here, but another thing that we haven't considered yet is that at any point, our number cannot be prime. So we could do kind of a brute force check every time and say, all right, when we get to a number, let's iterate through all its factors and make sure that its factors are only 1 and itself. But this can be kind of time consuming. So we could also use a sieve of Eratosthenes. I believe I spelled that right. So this is a really convenient way to look up a prime in constant time. So I'm not going to go super into the implementation here, but also know that we're going to be using this technique as part of our problem. So what we're going to do is we're going to iterate through all of our options, and we're going to place them in a heap. And we're going to use this heap along with our Dijkstra's algorithm. And then in each step, we're going to also use our sieve and say, all right, we've found a new potential number. Let's check in our sieve. If it's prime, we know that we cannot explore it any further, so we'll just continue past. Otherwise, we could place it in our heap, prioritizing the minimum cost options and kind of exploring from there. So this is all pretty high level and pretty theoretical, but I think as we get into the code, it will make more sense as to what exactly we're doing with these algorithms and data structures and how we're using them. So the first thing we do in our code is we're going to set up our sieve. So essentially what our sieve is going to do is that we're going to have a list of primes in the range from 0 to our limit. And the constraint for this problem is up to 10,000, so I just include 10,001 characters. So we're going to start with the factor of 2, and we're basically going to, for each factor, right, we're going to see if this is a prime. If it is a prime in our current primes array, what we're going to do is we're going to, for every factor or for every multiple of this number, we're going to say that it's not prime. So for example, we're starting at 2. We'll say that, okay, 2 is a prime number, so I know that any multiple of this, say 4, 6, 8, 10, 12, cannot be prime. So that's what I'm doing in this loop. Then I would increment this p-value by 1. So now I would do 3. I would say, is 3 prime? Yes, so any multiple, 6, 9, 12, 15, 18, 21, I know these are not prime. So essentially what we're doing here is we're just pre-computing all these different prime values that later on, when we need to ask if a number is prime, we can just look in here rather than calculating it on the fly. So pretty helpful tool to save some time. Then we're going to do our actual Dijkstra's algorithm. So there's a couple of cases we want to consider. So a special case is where n equals 1 and m equals 1. This is kind of an interesting edge case I ran into while I was solving this problem. So here we just return 1 because it doesn't really fall into the logic of any of the rest of the problem. Then another interesting edge case is that the n that we're given might already be prime. And we know that at any point, this number cannot be prime, right? So if we're starting with a prime number already, just return -1 because we know that it's impossible. So then what we're going to do is we're going to set up our Dijkstra's algorithm. So what we're going to do here is we're going to have a heap, and each element in the heap will have 2 elements in it. So this is going to be our cost, and we're starting at 0 cost, and then we're also going to have whatever current number that we're looking at. So while we have things in our heap, we're going to pop them off. And if at any point the number that we're looking at is equal to our target, we can return the cost we found so far plus whatever number we're looking at, right? And we're returning cost plus number because this is the cost that we found for the rest of the problem, but we also have to include our current number as part of our cost. So we're just going to return both of those values. We're also going to use a set just to make sure we're not repeating numbers that we've seen already. So then we have to do some kind of ugly string manipulation logic. So we're going to convert our number into a list, and then we're going to iterate through all the digits of that list. So we create a copy of the list. Then we basically do the logic where if the digit's 9, then we can just set it to 8, decrease it by 1. Then we basically make it into a string. We check if that new number is prime. So if it's prime, we do not want to put it into our heap because we don't want to consider it. We also want to check and see that it's actually a valid integer, right? Because it's potentially, we might decrease the first number to 0. So in this case, that's not really a valid integer. We can't have leading zeros for an integer. So we also check that in each case. We do a similar thing for our 0 case. So if our digit is 0, we just increase it to 1, do the same logic. And then finally, our last case is where our digit is between 1 and 8. So in those cases, we have to try both. So we either decrease the digit down from where we're at or increase it by 1 as well, and then try both those cases with the same logic. So this is a lot of pretty ugly code, but essentially what we're doing is we're just iterating through all the digits and trying them all, seeing if they're valid, and if they are, we're placing them in our heap and allowing the Dijkstra's algorithm to calculate the lowest cost possible path to get to our target. So let's submit this and make sure that it works. and it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.